Welcome back. This is the second and probably final segment for section 2.3. 2.3 really isn't that long, and you could probably make it much longer, but I don't know. Like I said, the tasks that it asks you to do, which is working with a calculator to compute angles or trig functions, is pretty basic operation, but worth indicating. So I'm gonna just dive into the next part. As I described at the end of the last segment, I had said that we're going to be looking at doing the reverse. Like before, we were taking, like a known angle and trying to find a trig function value for it, given that we can use a calculator in some way. We had to often use some trigonometric identities to get to the value because the calculator doesn't have everything. So the next question is, what about if we know the value of a trig function and want to find an associated angle? Okay, so that we've actually looked at that problem in the previous section where we said, hey, if what values between 0 and 360 degrees does sine of theta equal -1/2, right? Those kinds of problems, and we even had one on the test. So the question is there a way to do this when the numbers are kind of obscure? Because yes, if you recognize, okay, sine of 30 degrees is 1/2, so in quadrant 3 and 4, sine will be negative and have a value of -1/2 where the reference angle is equal to 30 degrees, etc. But that's kind of a complicated process. Is there a way that we can streamline it? And the answer is yeah. I mean, we can use calculators to do it. But here's the problem: is that we have to be somewhat careful about inverse functions because they're kind of a little bit bizarre. But we have a lot of time to really dive into this when we get into chapter 6. But for now, we're going to be looking at things that have small values, say typically between -90 degrees and +90 degrees, maybe even 180, but it'll only ever be in 2 quadrants. So let me just kind of make this statement. This involves the use of so-called inverse trig functions. Now, it might be a little bit hard to see, but on my calculator, if you look right above the sign button, there's something that says SIN, and it looks like it's got a superscript of -1. Same here with cosine, superscript -1, tangent, superscript -1. Those are the inverse functions. Now, remember that when we looked at the notation for how we raise a trig function to a power, there was kind of this, we just sort of put it in this weird, for whatever reason, there's a lot of inconsistency in the way that the notation is done for trig functions, and I honestly have no idea why. But if you recall, cosine, of some angle squared looks like this, and that means you take the cosine of the angle, you compute that first, and then you square it, right? So what does this mean? Let me just use a different variable because that turns out that this is not an angle. So what does this mean? You might think that it's just 1/. I mean, that's how this symbol is used sometimes, is to say, oh, well, that's to the -1st power. So that's, instead of repeated multiplication, that's repeated division. So I'm just going to say right? This is what you might think it is. And I'm going to be emphatic and say, no, that is not what that means. Okay, what this means is that there exists an angle for which cosine of that angle, let's say it exists an angle theta for which cosine of that angle is equal to x. Okay, that's what this is saying. When you write cosine, inverse cosine of x equal to theta. X maybe is a known number and you're trying to find the angle associated with it. These two statements are kind of equivalent. The only difference is that this is cosine is not a so-called one-to-one function, so it fails the horizontal line test. And so there are many angles that might produce this value, whatever it happens to be. And so when we use the inverse function, we have to kind of restrict the domain, say, well, we're only going to, or restrict the range, so we're only going to get certain angles coming out of here. That's something probably for another time. This is not really the format to be talking about that at length. But do understand that this is kind of a weird situation, and you should, anytime you're being asked to take a inverse trig function, you should take at least 15 seconds to say, what am I expecting to come out of this? What kind of an answer is going to be reasonable? Because it's easy to convince yourself that you have something much more strange going on. Okay, so that's sort of the first pitfall, is that it's the notational error. People they think that maybe that's, that cosine, inverse cosine is 1 over, which, then would be secant, which it's not. Another issue is what about, inverse cotangent, inverse secant, and inverse cosecant? How's that supposed to work? Because just like there's no secant, cosecant, or tangent button or cotangent button on your calculator, there's no inverses for those either. So let me just do this. There is one and only one identity that we will talk about in this entire semester that involves inverse trig functions. Okay, so remember, what we're wanting to do is we're wanting to say, let's take cotangent, for example. Inverse cotangent of x equal theta. So we have x, we have a ratio, and we want to find the angle that's associated with that. Okay, this is sort of an equation we might be trying to solve. If we had an inverse cotangent button, we could just plug in whatever x is and take that, and then bam, out you go. However, there's only the inverse tangent that's relevant in this case, and so we have to find a way to make this make sense. So much like we have this equivalent, I'm going to just kind of say, okay, well, this statement is equivalent to the statement cotangent of theta is equal to x. Now we know x, we want theta, but cotangent of theta is equal to 1 over tangent of theta, right? That's an identity, fundamental identity. So we can combine these two equations, and we say, well, whatever this angle is, which I'm trying to find, right, then 1 over tangent of the angle is equal to x. And remember, x is the known value. So tangent of theta is equal to 1 over x. That is equivalent to a statement that inverse tangent of x is equal to, inverse tangent of 1 over x is equal to theta. So these two statements are equivalent. And this is kind of gives us a secret as to how to compute the inverse cotangent. So this is really kind of a weird thing because people want to say, oh, well, I just, you know, I take the inverse tangent, I take 1 over. That does not produce the right result. Okay, and in fact, it produces something that usually is undefined or doesn't make any sense or whatever. So if you have a reciprocal function, inverse trig reciprocal function, be it inverse secant, inverse cosecant, inverse cotangent. I'm just going to summarize here. So inverse cotangent, or sorry, inverse cotangent of 1 over x is equal to the inverse tangent of x. And I got to be careful here because there's some range errors. I'll have to say if x is greater than 0. I'm going to come back to this in later sections, but there is a sort of qualification here that has to be addressed. Inverse cosecant of 1 over x is equal to inverse sine of x, and inverse secant of 1 over x is equal to inverse cosine of x, or vice versa. I mean, this could be the 1 over. This is the number that generally you're given in the problem, and this is the conversion you have to do using a different function to be able to calculate the angle. So that's kind of a sort of a big scale theoretical idea. Let's show it in practice so that we can hammer that home a little bit. So remember, we're trying to find angles that, let's see, I'm on page 3, section 2.3, page number 4. So let's say find, so for what quadrant, for what angle theta, and I'll even explicitly say that it's in quadrant 1, is the following true? I'm going to do some that are a little bit easy, and then I'll do ones that involve this reciprocal idea. So let's say sine of theta equal to 1/3. Let's say tangent of theta equal to 7. Then let's do cotangent of theta equal to 5. How about secant of theta equal to 4? Okay. Now none of those are the values that we've said these are exact values for certain angles. So we're going to have to use a calculator to get them. And each one works a little bit differently. And just to kind of show this, I'm going to maybe do a last one where I say, what happens if, let me make it cosine. So cosine of theta equal to 3/2. Hopefully you recognize that that's a problem. Okay, so the task here is to find an angle. We have the ratios. We need to find the angle. Now, you will not be able to use the techniques out of chapter 1 to do this. Like I said, this is simply going to come down to a calculator exercise in most cases. So let's start with the first one. So if sine of theta is equal to 1/3 and theta is in quadrant 1, which it is, then theta will be equal to the inverse sine of 1/3. Okay. This is a solution. There are many, many values of theta that will do this, but this is the one that we're being asked to find. So let's try that. So 1 divided by 3, so I got 3 repeating, and then I'm going to take the inverse sine of that function. Now this is in degree mode, so that's a decimal degree. So this is so theta is equal to 19.47122.063, etc. degrees. And like I said, we haven't really figured out how to round things off yet. What about tangent? Very similarly, tangent of theta equal to 7 implies that theta is equal to the inverse tangent of 7. Easy enough to do. We take 7, and then we take the inverse tangent. We get 81, so theta is equal to 81.86989765, etc. degrees. Okay, those were the easy ones. What about the cotangent of cotangent of theta equal to 5? So cotangent of theta equal to 5, and because of this argument that we just made, I think I can kind of skip ahead and say, well, that implies that theta is equal to the inverse tangent of 1 over 5, or just 1/5, which is 1 divided by 5 should be 0.2, and then I take the inverse tangent, and I get 11, so theta equal to 11.30993,247. And if you don't, and of course there's extra digits, but if you're a little unsure about this, you can just plug that number back in and then take the tangent and see if you get the same value. Because it is easy to fat finger some things, but so be it. We had D. We were doing this with secant. So secant of theta equal to 4 implies that theta is equal to, and again, this is going to be the inverse reciprocal function of the reciprocal of the value. So this will be the inverse cosine of 1 over 4, which will be 0.25, 1 divided by 4, right? And then we'll take the inverse cosine, and there's our degree measurement. So theta equal to 75.52248781 degrees. Okay, now the last one is a trick question. So cosine of theta equal to 3/2. Why is this a trick question? Well, because it's because the 3/2 is outside of the range of cosine. There is no real angle that you can plug into this equation and ever get cosine to be 3/2. This does happen from time to time. The textbook will kind of throw these problems at you just so that you learn to recognize them or whatever. But like I said, they do happen occasionally. There's usually, when you're dealing with physical problems that involve trigonometric functions, when things get to a critical value where they start to exceed the range, sometimes there's physical properties. There's something called total internal reflection that you have in lenses and stuff that actually are where the solution breaks down. So there is no answer to this. There's no angle that will work, and this can be like sort of you can waste a lot of time trying to do it, because if you look and say, okay, well, if I were going to follow the regular rules, I'd say, all right, so this is the same thing as saying inverse cosine of 3/2 is equal to theta. So when I put 1.5 and then I try to take the inverse cosine, I'm going to get an error. And the error is because there's no such angle that will do that. So you could either say no such theta. You could maybe use a different symbol where the solution set is the empty set. You know, there's other kinds of choices for saying that. And as long as I can understand what you're trying to say, I think that's fine. Okay, so last topic, and I know I'm getting a little bit long here. Hopefully I'm not too far over, but I do want to finish this section. I want to look at an equation that has quite a bit of algebra in it, as well as some trig issues. I think it's kind of get back here to center. Okay, so in the textbook, or at least in a previous version of the textbook, there was kind of this bizarro formula that involved braking distance, or how far you would have to apply brakes in order to go from one speed to another. And it looks a little intimidating because it's this big, long, ugly formula. You have d equal to 1.05 times the quantity v1 squared minus v2 squared all over 64.4 times k1 plus k2 plus sine of theta. And so let me just quickly summarize what this is telling you is that, okay, so the distance measured in feet is equal to a constant that really these constants are so all the units work out, right? Where your initial speed, V1, is measured in feet per second. And V2, your sort of final speed, is measured in feet per second. Again, this is another constant to make the units work right, which is why I don't know why they don't combine it in a single constant. Then you have this two numbers that are associated with the friction, two different kinds of friction, one of which is sort of rolling friction from the tire, and one that's from what's called static friction between kinetic friction between the brake plates and the disc. I want to take this back. The speeds for this formula to work right, the speeds have to be in miles per hour, but the distance is actually in feet. And then sine theta. What's theta? Well, this is kind of whether you're going up a ramp or down a ramp. So if you imagine, here's sort of the scenario. That's a horizontal line. If you've got a car that's going down a ramp with some negative angle, it's going to be a little harder to get it to slow down than if it was going up a ramp. And so the SIGN of this is critical, because if theta is negative, then sine is negative. This number is actually a smaller number. And so a number divided by a smaller number is actually a larger number, anyways. So I don't want to make this overly complicated, because this problem is actually pretty trivial in the way that it's written in the textbook, because they will ask you things like, they will give you what the values of a lot of these numbers are, and then say, okay, find find D. It's literally like plug and chug. So so if a car comes to a complete stop, what does that tell you? Well, remember, this is the final speed in miles per hour. So that's just V2 equals 0. Suppose the initial speed is 55 miles per hour. So you're trying to come to a complete stop from going, 55 miles an hour. And you're going slightly uphill, so theta equal to 3.5 degrees, where the coefficient of friction between the disc plates and the disc itself is 0.4, kinetic friction, and rolling friction on the tire is coefficient of 0.02. Find the distance in feet, okay? So this seems like this is a really kind of, because you've got this bizarro formula, it seems like this is a really challenging problem. It really is not that challenging. So distance is equal to 1.05 times 55 squared minus 0 squared, all divided by 64.4 times the quantity 0.4 plus 0.02 plus the sine of 3.5 degrees. Plug and chug, folks. There's nothing exciting going on here. So when usually if I'm doing this, I want to work on the numerator and start inside the parentheses, mash those things together, take the most complicated part and then move forward. So I'm going to start with 3.5 degrees and take the sine of that. Okay? So that's the sine of 3.5. And then I'm going to add 0.02, add 0.4, and that's the total. So that's that parentheses right here reduced. Now I'm going to multiply that by 64.4. And since it's in the denominator, I'm going to now take the reciprocal. I'm going to multiply it by, well, this is going to reduce to 55 squared. If this was a number, I might use a parentheses. But so I'm multiplying by 55 squared. And then I am multiplying by 1.05. So there's our answer in feet. And since, like I said, we still don't know how to apply significant digits, so I've got a distance of 102.527.392 feet, which it turns out that, since we will be close to doing this soon, I mean, these things only have one significant digit, so that's kind of a little disconcerting, because that makes the answer 100 feet. But we'll talk about those rules in the next section. So this, I think that maybe there's a problem in the text that's a little more complicated, where you have to find the angle. So you're given the distance and you have to find the angle, possibly, or something along those lines. Sometimes they can get a little more complicated, but that's where your algebra skill comes to bear. When you're trying to solve an equation that has a trig function in it, where the argument is the variable, you have to use algebraic techniques to isolate the trig function, which is very analogous to the way that you solve, like, say, absolute value equations. But anyways, I'm going to let you give it the old college try, and if you have any questions, then feel free to ask them when we have a chance. Okay, that's it for section 2.3. I will see you in the next section.